All right, welcome back. And one of the big problems that I have run into in the idea of trying to teach probability over time is this idea that the formulas are really just confusing and difficult, and mainly they make students think about this. So, in order to keep you from screaming too much, I really don't like to focus too much on a lot of these crazy symbols and everything, and it's easy to get bogged down in what that means and trying to translate mathematically. So for this video, the two rules that we're going to look at, the union rule and the complement rule, we're going to keep it pretty simple and straightforward. The union rule is the probability of this or that happening. So it's two or more events, and either one event could occur or the other event could occur or other events. Now the catch is you have to watch out for the dreaded double counting, as I can't write all of a sudden once again. You need to watch out for the dreaded double counting. And that's something that you'll learn to pick up as time goes by with a lot of practice. On the complement rule, what you need to know about the complement rule is the probability of some event not happening. And if you think about this, it makes a lot of sense, because when we talked about complements of sets, we talked about everything that was in the universal set that wasn't in the set named. So we're going to be going through an example or two where it might be easier to find the probability of an event happening and then subtract that from 1 to figure out the probability that it doesn't happen. Let's take a look at a few situations here. Okay, and we'll go back to a standard deck of cards, and 52 cards, once again, 4 suits. Spades and clubs are printed with black ink, and diamonds and hearts are printed with red ink, 3 face cards, jack, queen, king, etc. So the problem that we run into here with A is that we run into a situation where we have events that are not mutually exclusive, that they have outcomes in common. So, for example, on the red cards, we know that there are 26 red cards in the deck. And we also know that there are 12 face cards in the deck. So if I'm trying to find the probability of drawing a red card or a face card, it seems obvious to add those two together. However, when it comes to red cards being face cards, there are 6 cards: a jack, a queen, and a king of hearts, and a jack and a queen and a king of diamonds. Those are face cards that also just happen to be red. So in order to stop myself from double counting, I need to take out those 6 cards, because I counted them once in my 26 and once again in my 12. So when I get all this put together, it's going to work out to be 32 over 52, which reduces down to 8 over 13. So this is what we mean by double counting. We double counted these in order to make sure, we have to take those out in order to make sure that we don't accidentally count them twice in our process here. Okay, let's go over to part B here, and it says the card is less than a 4 or it's a heart. Now, just for the purpose of this particular example, we are going to say that aces are low. So a card that is less than 4 could be an ace, a 2, or a 3. And there are 12 of those in the deck. And the other or part here is that we're looking at or a heart. Well, 13 hearts in the deck. And please forgive me, I hope you caught what I'm just catching right now. This shouldn't be 12 out of 13, that should be 12 out of 52. Whoops-a-doodle. Okay, there we go. But we have to remember what we've double counted. we have double counted 3 cards that are both hearts and less than 4. That's the ace, 2, and 3 of hearts. So I have to subtract those because I've counted them twice. That gives me 22 out of 52, or 11 out of 26. So that's a couple quick examples on how to use the union rule and come up with the probability when you have to watch out for double counting. All right, now let's take a look at the card being not a spade. Well, I have to be honest with you that sometimes finding the probability of something being a spade might be easier. So the probability that a card that you draw is a spade is going to be 13 out of 52, or 1/4 when you reduce that all the way down. 13 spades in the deck out of 52 cards. Now, if I want to find the probability that the card is not a spade, then to answer this question, what I need to do is basically find the probability that this event, E, is a complement, actually. So it's going to be 1 minus 1/4, and 3/4 is the probability that the card is not a spade. Okay. Now for part D, lucky for us, we've already got our answer in place here. It's not going to be too hard to do. If I need to find the probability that the card is not red or a face card, well, I already know what the probability is that it is red or a face card. We did that back here in part A. So let's not overcomplicate this. And when we see the magic word not, when we see that magic word not, that needs to be a signal that we're dealing with complements here. So to find that probability, it's going to be 1 minus 8 over 13, because again, that's the probability that it is a red card or a face card. And there's the probability of 5 out of 13. Another common situation that we'll run into in rolling 2 dice is the fact that there are actually 36 outcomes. And they are listed here on this chart that you see that I've got pictured here, where the red die represents the first die rolled and the white one represents the second die rolled. So you can roll a 1 on the first die and then pair that off with each of the 6 possibilities on the second die, or you can roll a 2 on the first die and pair that off with each of the 6, etc., etc. So that's why there are 36 outcomes. Now, a really common occurrence, especially if you like board games, is to roll 2 dice to maybe move your token along the board. I know if you're playing Monopoly, that's a pretty common thing to do, is to roll 2 dice. So you'll notice that there is an interesting little symmetry with this. There is exactly one way to get a 2 on these dice, and that's to roll both 1s. That's 1 out of 36 probability. If you look down here in the other corner, there is exactly one way to roll a 12, and that's to get a pair of 6s. 1 out of 36 probability. Now, as you go towards the middle of this chart, you'll realize that in the middle, all of these outcomes that my green arrow is pointing to on your screen, all of those have an outcome of 7. 7 is the most likely number to be rolled on a pair of dice because it's 1 out of 6. Well, how did I get that quickly? Well, there are 6 outcomes here that total 7, and there's 36 possible outcomes total. Okay, so that's just a quick little interesting idea of the symmetry of this situation, and if you did a little study on your own, you'd be able to come up with the different probabilities and notice that it starts at 1 out of 36 and works its way up to 6 out of 36 and then back down to 1 again. Pretty interesting situation and kind of a fun thing to look at, especially if you're sitting on Indiana Avenue and you really do not want to go to jail. Okay, so let's take a look at this idea. The 2 fair dice are rolled and find each probability. All right, now the first die shows a 2. Well, let me go ahead and highlight those particular outcomes for you right here. They will be right across this row here if the first die shows a 2. So that would be 6 out of 36 possible outcomes. Okay. Now we also want to look at the idea that the die shows a 6 or a 7. Okay, well we know that the ones with a 7 are right up that diagonal, and the ones that are a 6 are also up that diagonal that is right above it. So we've got all of these ones that I'm highlighting and kind of shading in green that you can see that are either 6 or 7. Just not this one down here, because that one is an 8. So we need to come back and give that just a blue shading. Is what it needs. Okay, and you will notice that as we count it up, there's going to be 6 outcomes that have a 7 and 5 outcomes that have a 6. So that's going to be 11 out of 36. But you will notice something. You will notice that I have managed to double count 2 of those outcomes right here. I double counted 2 of them. One in the blue because the first die is a 2, and one in the green because they total 6 or 7. So I have to take away those 2, otherwise I'm in some trouble here. And that's going to give me 15 out of 36 when I summarize this all together. And since it's divisible by 3, I'm going to go ahead and drop it down to 5 out of 12 as the probability. Okay, so that's one way to think about how you would figure that particular set of probabilities. And if you need to print out a couple of those charts and mark them up to make your life a little bit easier, by all means, please do. It's a there's no rule that says that you can't do that to help your cause on things. So we're going to get the highlights out of here, and we're going to go on to the next question here. All right, so now we look and turn our focus on the next question, which says the sum is either 3 or 10, and those are mutually exclusive. Well, yes, of course they're mutually exclusive, because the 3's are going to be up here in the upper corner, and the 10's are going to be down here where you could get a 6 or a 4, a pair of 5's, or a 4 and a 6. So the probability that you roll a 3 is 2 out of 36. The probability that you roll a 10 is going to be 3 out of 36, and that's going to be a grand total of 5 out of 36. Now, because I didn't double shade anything, I don't have to subtract anything. I didn't double count by accident. All right, now let's talk a little bit about this idea of finding the probability of not rolling a 7. And once again, it just might be a little bit easier if we found the probability of rolling a 7 first and then working our way back from there. Okay, so the probability of rolling a 7, as we discussed on the previous slide, that's going to be 6 out of 36, or 1/6. So the probability of not rolling a 7 is going to be the difference between 1 and that probability, which is 5/6. Not all that hard to do. Complements are pretty easy. The union rule is a little bit more challenging. All right, now sometimes a Venn diagram is very helpful to answer some questions. And I'm sure all of you have seen a Venn diagram before. We didn't touch much on them, but I am going to go ahead and wander through this example here to share with you that with a Venn diagram, we've got this area where we're representing 2 different sets, and this one circle represents one set, and the second one represents another set. Here in the middle is where they intersect, and out here is kind of like our universal set, but it is not in either one. So let's kind of go through this problem and see if we can come up with some answers. Now, if you're using this for probability, the key thing that you need to remember is all regions add to 1. That's going to be the key thing that we need to remember here. Okay. All right, so Susan is a college student, receives heavy sweaters from her aunt at the first sign of cold weather. And Susan has determined that the probability that the sweater is the wrong size is 0.47, and that the probability that it is a loud color is 0.59, and the probability that it is both is 0.31. Okay, well, let's kind of label these sets here. I'm going to start with saying the W being a wrong size and C being a loud color. And if it is both, then it's 0.31. Well, now how do we figure the rest of the regions? Well, this is actually not too bad. Here's the way that we figure out the probability that it's just the wrong size but not a loud color. We know that the probability that she has a wrong size is 0.47. So that represents this entire circle right here. So if 0.31 of it is in the middle, then I have to do some subtraction. And I get 0.16 as the probability that it's just a wrong size only. Okay, now let's take a look and do the same thing for the loud color. If the probability that it's a loud color is 0.59 and 0.31 is taken up there, then it's going to be 0.28. Okay, so not bad. And now I need to come up with what's the probability that it is a good size and not a loud color and something that she won't have her classmates make fun of her. Well, in order for me to do that, I need to add all of this together. So 0.16 and 0.31 and 0.28 added together. Let's see, that's 15, that's going to be 0.75 is the way it looks if my math is correct. So 0.25 is on the outside. All right, now that we've got all those ironed out and we all know exactly how much probability is at work here, we can go ahead and start answering these questions. So the first question is, what's the probability that the sweater is a correct size and it is not a loud color? Okay, so it's got to be the correct size. That means it isn't a wrong size. So it's outside the area where it is the correct size or incorrect size and the color. So I think it's going to be 0.25. Only 25% of these sweaters are going to have a good size and a loud color. Not a loud color, rather. Okay. What's the probability that the sweater is the correct size or it is not a loud color? Okay, so that's a little bit different of a question here. Well, not or is a correct size means that it's completely outside of circle W. So 0.28 and 0.25, that is 0.53. Now, a loud color, on the other hand, is going to be outside circle C, not a loud color. So 0.16 and 0.25, that is 0.41. But you might notice that when I did that, I double counted the 0.25. So I better subtract